Hope screen is visible to everyone.
Yes, sir.
Yes, sir.
Okay. So in the previous class, we begin with the structure of FIR systems. So here they are going to provide the what is the system function. So what is the system function? How it is going to behave for the input, and what is the required or desired output it is going to give. So based on that equation, so we go for the structure for FIR system. So here we are going to have three types of structures. One is direct form one and cascaded and linear phase, as well as we have lattice structures. So here the direct form one, it is realized using this the system function h of z. So it is nothing but what? It is the difference equation what we are going to get regarding that system function. Then we have the cascaded realization. Then we had discussion about linear phase. So linear phase, once again, it is having the whatever the function, it is the length of filter. If it is even condition and if it is odd condition. So we had those structures. For even case, the circuit will be, the structure will be like this, and for odd, it has different structure. Okay. Then we had solved some examples on these structures. One, response. So the impulse response, if we go for one of the example, it is the system response. If it is h of n, it is given. First, we need to go for the Z transform of given structure, given impulse response. Then we need to go for the output of that one, that is the ratio of output. The impulse response is nothing but the ratio of output by input. So output is nothing but what? It is the function of inputs. Then once we are going to take the inverse Z transform of the output, and we are going to draw the circuit structure according to that equation. So go for the next concept is the lattice structure. So the concept of this structure, it is meant for if you want to upgrade the order of the filter, order of the filter. So it is nothing but what? The length of the filter is nothing but order of the filter. So if it is for in linear phase, or if you go for the direct form one or the cascaded form. So what is going to happen if you increase the order of the system? Obviously, it is going to give the structure is going to be updated. But if you go for the linear phase structure, if n is even or odd condition, the order of the filter, if it is even or odd. So if it is even, the structure is different. For odd, the structure is different. So here, what we are going to observe in linear phase, if the upgradation is there in the filter order, obviously the complete structure is going to be modified. So how to resolve this concept? By retaining the previous structures as it is. Okay, so you are designing for m equal to 1, m equal to 2, m equal to 3. Okay, so if you increase the order, then the structure is going to be changing based on even order and odd order. But to overcome this drawback of this linear phase, we are going to introduce with the lattice structures. So how we are going to draw the lattice structures? So go for this one. The lattice filters are computationally very efficient than other filter structures, and they are less sensitive to finite word length effect than direct form filter structures. Okay, let us begin with how to derive the lattice structure. So let us go for a transfer function of an FIR filter, which is given by the system function, that is h of z. Here we are going to label that one as e of z. Okay, don't get confused about these labels. So based on the structures, we are going to use different labels. So the transfer function of the system function, it is given by the ratio of output by input y of z divided by x of z, which is equals to a of z, which is given by 1 plus. So instead of going for I is equal to 0 to m minus 1, okay, here we are going to deal with 1 plus summation I is ranging from 1 to m. It is am of I, it is z to the power minus 1. That is nothing but the output, the transfer function in the form of z transform. Okay. So here we have the transfer function. It is given by y of z divided by x of z, which is nothing but 1 plus summation I is equal to 1 to m am of I into z inverse. So this equation for m is order of the FIR filter, where am of 0 means the coefficient of first element, it is always 1. So when m is equal to 1, if you consider in this equation, when m is means the order of the filter, it is 1. Order of the filter is 1, then the y of z divided by x of z is nothing but 1 plus the coefficient of that x element, the first element, it is a1 of 1 z inverse. So if you take only output, that is y of z, is nothing but the function of input with coefficients, that is given by x of z plus a1 of 1 z inverse into x of z. So if m equal to 1, nothing but the order of the FIR filter is 1. So order of the filter is 0, obviously output is equals to input itself if it is 0. Okay, if it is order is 1, obviously it is going to wait for the previous element of the x. So that is known by what this term, x of z into z inverse, nothing but previous one element, okay, of the input signal, present and previous one. If order is 2, obviously present and previous 2, and it goes on, the filter order, it goes on, increases. So this is for m equal to 1. If you go for the taking, if you want to take the inverse Z transform for designing the circuit, obviously the taking inverse Z transform, we are going to get y of Z. The inverse Z transform, that one is y of n, and x of Z is nothing but x of n plus the coefficient remains as it is, a1 of 1, and the product, the inverse Z transform of x of Z into Z inverse is nothing but the previous element by 1, that is x of n minus 1. Okay, so the lattice structure for the above first order difference equation, it is given by this diagram. So this is a first order lattice structure. So if you go for this one, here we have the x of n is given into, obviously before going to this explanation of this one, let me explain. It has two channels. It has two output channels. One is called as upper channel, another one is called as lower channel. Okay, it is for only first order lattice structure. So here the both channels are connected, they are cross connected with coefficients. Okay, for that particular order of the filter. Okay, so each stage in the lattice, each stage here it is cross connected with the line value, the order of the filter. Okay, so it is only first order, hence it is they are cross connected with the coefficient k1. So what is this k1 and these labels? You will come to know when we go for the equations. So the first order lattice structure, as it is shown, has two outputs, that is f1 of n and r1 of n. And f1 of n, it is known as upper channel output, and r1 of n, it is known as lower channel output. Okay. So, and the subscriptions denote the filter orders. So this is called the single stage lattice. So if it's first order, it is single stage lattice. So if you go for the inputs to the first order lattice structure, by seeing this structure, you can define what are the inputs. So here the upper channel has the input f0 of n, and lower channel has the inputs r0 of n. So if you go for this one, the f0 of n and r0 of n, for both upper and lower channels, it is the input, original input x of n. Therefore, the outputs, by seeing this diagram, the cross connections are nothing but the sum of two lines with coefficient values. So if you go for the f1 of n is nothing but the f0 of n, which is coming as the input to the upper channel, plus the k1, the coefficient of this lower channel, k1 into the r0 of n minus 1. Why it is n minus 1? Because there is a delay in the input. So r0 of n is coming with the delay at the summing point. So therefore it is r0 of n into z inverse is nothing but the inverse transform. Z transform is going to give the answer as r0 of n minus 1. Okay. So if you go for the lower channel output, that is r1 of n is nothing but this r0 of n minus 1. Okay, that is r0 of n minus 1 plus f0 of n, it is multiplied with k1. So k1 into f0 of n plus r0 of n minus 1. So these are the two outputs what we are going to derive. Here, by considering these two equations, that is nothing but this f1 of n and this y1 of y of n, we may conclude that the coefficients k1 is nothing but what. So in the diagram, we are going to use the different labels. K1 and k is nothing but coefficient of that particular lattice structure, okay, that stage, and f0 or f is nothing but the upper channel and r is nothing but the lower channel. Okay, for initial steps, it is f0. Next comes f1, means first order, second order, f2, third order, f3, and up to fm. So the length of the filter, it is m, or you may say n, capital N or capital M, whatever the length you are going to specify, we are going to have those upper and lower channel outputs. Okay. So initial stage, obviously zero order, nothing but what? It is f0 and r1. First order f1 r1. Second order f2 r2. And here for first order, the coefficients are the cross connected values. Line values are k1 for first order. For second order, it is k2. Third order k3, and so on. Okay. So this structure is going to be increased as we are going to increase the order of the filter. So if you compare these two equations, means what are the values you need to consider for k1? So it is nothing but what? Is by comparing these two, we come to know f1 of n is nothing but y of n. Okay, means upper channel output is the exact output from the system. And what about this value of k1? K1 is nothing but the coefficient of x of n minus 1, that is a1 of 1. Next, if you go for m is equals to 2. So m is equals to 2 is nothing but transfer function y of z divided by x of z is nothing but 1 plus summation I is equals to 1 to m. So m it is 2 now. M is 2, therefore it is I2 of 1 z inverse plus I2 of 2 z to the power minus 2. So if you go for only output, the only output it is y of z is nothing but x of z plus a2 of 1 into x of z inverse plus a2 of 2 into x of z into z to the power minus 2. Now, if you take the inverse z transform, the exact output from the system it is y of n, which is equal to the inverse z transform x of z is x of n. The coefficient remains as it is, that is a2 of 1, and the product of x of z into z inverse, it is nothing but x of n minus 1, and x of z into z to the power minus 2 is nothing but x of n minus 2. Okay, then if you consider here y of n is nothing but f1 of n plus k2 of r1 of n minus 1. Then substituting these equations. So if you consider the y of n, output is nothing but f1 of n plus k2 of r1 of n minus 1. Then by substituting equations, these two equations, f1 and r1 values, f1, okay, f1 and r1 equations in that equation. So we can expand that equation by y of n is nothing but f1 of n, that is f0 of n. Since I am talking about the next stage of this one, the next stage here. So what will be the next stage here? So this is going to be continued here. If I remove these pointers, okay, what about next structure we need to draw here? So here f1 of n and r1 of n are going to act as input to the next stage. So once again, I need to continue here. Then I need to put a summer. I need to put a summer here. Then I need to go for the cross connection of these two with elements K2. Okay, similarly here, with cross connection, the coefficient is K2. So before going to this one, I need to put one more, one delay. So because the structure remains same, there is a delay. So what is going to happen at the outside the delay? It is R1 of n minus 1. So we are going to observe here, it is R1 of n minus 1 we are going to get. Okay, so here it is f1 of n, f1 of n. So what we are going to get here? It is what? It is exact output y of n. That is nothing but what? f2 of n and r2 of n. So it goes on continuous. So we are deriving that step. This step we are designing. This step we are designing for that thing. So if you consider y of n, so it is f1 of n plus a2 of r1 of n minus 1. Therefore, we are going to get it is f0 of n, 0th order, k1 r0 of n minus 1 plus k2 of the remaining product. What we are going to get, that is k1 of f0 of n minus 1 plus r0 of n2. Once you substitute what is r1 of n minus 1 and what is f1 of n. Okay. So therefore, it's going to minimize to the term f1 of f0 y of n is nothing but f0 of n plus k1 of r0 of n plus k1 k2 f0 n minus 1 plus k2 r0 of n minus 2. So if you go for deriving this equation, so here it is drawn directly. Okay, we are not showing any mathematical steps, the substitution and removing the brackets, taking the common terms. By performing all those calculations, we are end up with the y of n. So since we know what is f0 and r0 from the previous time, so the f0 and r0 is nothing but what? The input signal x of n itself. So we come to know what is the actual y of n. So y of n, you just replace what is the f0 and r0. Okay. So if you go for f0 of n is nothing but x of n, and what about here? So if you take the common terms, it is x of n minus 1. You just replace what is r naught. Okay, r naught of n, if it is x of n, what is the r naught of n minus 1? Obviously, it is x of n minus 1. What about r naught n minus 2? Obviously, it is x of n minus 2. So substituting all those things, we may get the function of output. It is nothing but function of input, that is y of n is equal to x of n, the coefficient values of the lattice structure, that is k1 plus k1 k2, which is the coefficient of the previous element x of n minus 2. Then the another previous element x of n minus 2 has the coefficient k2. Then if you go for the actual, so k1 and k2 are the lattice structure coefficients. If you go for actual coefficient, those are nothing but what? a1, a2 of 1 and a2 of 2. So by having the coefficients, we have the a2 of 1 is nothing but k1 plus k1 k2, and a2 of 2 is nothing but k2. Okay, or by solving this one, we may have what are actual k1 and k2 equations. So k1 and k2 are given by k1 is nothing but the coefficient of first element a2 of 1 and divided by 1 plus the coefficient of second element, that is a2 of 2. What about k2 of 2? K2, it is nothing but the coefficient of second element, that is a2 of 2. Okay. So this means the lattice structure for second order filter is simply the cascade of two first order filters. So you can observe here what we have discussed, the next stage, second order. So first stage will be as it is. If you increase the order of the filter, so we need to go for the next stage. It is f2 of n and r2 of n with cross connected line values coefficients, that is k2. So k1 and k2 are representing the original coefficients from the input signal. Okay. So if you go for this one, think as we discussed here, this diagram we have drawn with the help of this one. So how to calculate the coefficient value based on these equations. So k1 is nothing but a1 of 1. What is k2? Okay, for first order it is k1. For second order it is the combination of both coefficients we need to concentrate. Okay. So for similar, if it is mth order, for mth order FIR filter, you can observe stages. It is up to m stages. Okay. So it is x of n is the original input, and we have both channels, upper and lower channels for m stage FIR filter. So here, if you go for the last coefficient, that is k term, it is k of m. So how you are going to get what is k of m and previous coefficient values? So to know those things, the standard formula are useful for converting the direct form 1 to lattice. Okay. So for m is equal to m minus 1 and up to 1, we may have the standard equation for this coefficient of lattice structure, that is k of m. K of m. So if you go for first order, k1 is nothing but what? K1 of 1. If you go for 2 order, it is k2 is nothing but what? K2 of 2. And third order, obviously it is k coefficient. It will be k3, which is equal to a3 of 3 itself. Okay. So if you go for the coefficient of the original signal, that is a of m minus 1 of ith term. A of m minus 1 of ith term, it is calculated by the standard formula, that is am of I minus of am of m into am of m minus of I divided by 1 minus km square. So if you look at this one, you can get. So here you can observe here what is a2 of n and a2 of 2. The previous element coefficient a2 of 1 and present it is a2 of 2. So how to calculate how this equation is coming across? So it is from the formula. Okay, it is a of m minus 1, the previous all elements, because we know the last element, that is am of m we know. What about previous element, coefficient? So to calculate that one, we need this equation between the range. I ranges from 1 to m minus 1. So from the above expression, we find that it fails in if km is equal to 1. So this is an indication that there is a 0 on the unit circle. So if km is 1, we can simply factor out this root from a of z, and above recursive formula can be applied for the reduction order system. So if you go for the overall concept for m is equal to 2, we can go for it is for the given expression, it is as we told discussed, it is k2 is nothing but a2 of 2. If it is 1, k1 is nothing but a1 of 1. Okay, and it goes on. All the calculations with respect to that coefficient, this goes on performing. Okay. But generally, some few definitions with respect to these coefficients. The am of 0 is always 1 and am of m is always am. And if you go for any ith term with respect to the coefficient for that particular order, it is am of I, it is nothing but am a of m minus 1 of I plus am of m into a of m minus 1 of m minus I. These are the three basic equations with respect to the coefficients of the input. Let us go for one example. So determine the coefficient Km of the lattice filter corresponding to FIR filter described by the system. What it is given? It is a second order filter. Okay, so we need to go for the second order lattice structure. So go for a solution. So we are given with what is this one? A2 of n, A2 of 1, which is equals to 2 by comparing the standard equation. So A of z is 1 plus 2 of z inverse plus 1 by 3 of z to the power minus 2. They are given what is the second order is I. So m is nothing but what? Order. So here the coefficients are m of 1, m of 2. So m is 2. Therefore, it is a2 of 1 and a2 of 2. So what is a2 of 1 by equation? It is 2, and a2 of 2 is nothing but 1 by 3. So we just recall the equations for calculation of the previous coefficients for first stage and second stage. So these are second stage coefficients. What about first stage coefficients? That is nothing but a of m minus of I, m minus 1 of I. So what is that m minus 1 of I? That is nothing but what it is? A1. Okay. So we need to go for this equation. What is Km? So obviously we know what is Km. M is equal to 2. So this equation will become what? A2 of 2. So if you want to calculate, we can calculate like this. So here m is 2 since we have two zeros in h of z. If m is equal to 2, we get A2 is nothing but A2 of 2, which is nothing but 1 by 3. So if m is equal to 1, we have A1 is equal to A1 of 1. Now, if m is equal to 2 and I is 1, therefore the A1 of 1 is given by A2 of 2. You need to go for these calculations, because here m is 2 and I is 1. When m is 2, obviously it is 2 minus 1 becomes what? A of 1 it is into of which element? First element. So you need to go on substituting the values. So it is what? A2 of this equation is what? A2 of 1 minus A2 of 2 and into A2 of 1 itself divided by 1 minus K2 square. So we need to go for that substitution here. Once again, if I substitute all the values in the respective in the given standard equation, so it is we're going to reduce to A1 of 1, which is equal to A2 of 1 minus A2 of 2 into A2 of 1 divided by 1 minus K2 square. Let us substitute or simplify the things. So here it is A2 of 1 is common. So A2 of 1 we have taken common and 1 minus A2 of 2 divided by 1 minus A2 square of 2. So because why it is K2? Because K2 is nothing but what? A2 of 2 itself. So it is A2 of 2 square. Then if you simplify the thing, you are going to get it is A2 of 1 divided by 1 plus A2 by A2 of 2. Now let us substitute all the values. We are going to get it is answer for A1 of 1 is nothing but 3 by 2. So once we got the original coefficients of input, it is A1 of 1 is 3 by 2, which is nothing but the coefficient of the lattice structure K1 itself. Okay, because K1 is equal to A1 of 1. So we got what is K1, we know what is K2, then we just put the diagram here. So here we are calculating what are the each stage coefficients in the lattice structure. Okay, so A coefficient is nothing but from the original signal coefficients. So we are converting those things into lattice structure. Okay, therefore, if you go for the two order lattice structure, it is given by x of n, the upper channel and lower channel. It is going to act as the input signal. Then the first stage, it is nothing but what? The upper channel it is f0, f1 of n, and the lower channel is r1 of n. So here the K1 is nothing but 3 by 2 and 3 by 2. Here it is K2 1 by 3 and 1 by 3 for both cross-connected line values. So finally we are going to get the y of n for second stage it is f2 of n and another lower channel it is r2 of n. So the main concentration it is what is the upper channel output. So this is the method how we can design the lattice structure. So in the design of lattice structure, we are calculating what are the coefficients of each stage. That is K value. Okay. To know that K value, we have to remember these equations. Okay. These two are the main equations what we need to remember. Okay. So sometimes what they are going to give, another problem is if they give the K terms they are going to provide. They are going to give the lattice structure and they are going to ask design the form. So direct from one is nothing but what? We are directly getting the coefficients of input A of M. Okay. AM what we are going to have in the direct form one, and what about K of M is nothing but the lattice structure coefficient. So how to calculate these things? So we will solve this one in the next class. So we will solve this example in the next class.